Hi everybody, this is our lecture video on the ANOVA hypothesis test. So again, just like the previous ones we've done, F-test, T-test, chi-square, it really is just a procedure that we're working through. So again, starting at step 1 and working our way through. So just like the last lecture videos we've done, let's run through sort of ANOVA in general, and then we'll look at an example together. So here's the reason why we use ANOVA. So when we were actually looking at two populations, we either used an F-test when we cared about dispersion or variability, and we used a T-test when we cared about the means. ANOVA, which is basically a short form of analysis of variance, is a way to actually look at more than two. So whether that's 3 or 4 or 10 data sets, we would actually run the ANOVA test. So just like there was assumptions for the t-test when we looked at means, there are definitely assumptions for running the ANOVA test as well. Again, we have that idea that your population should be normally distributed, and again, we're going to make that assumption in our course. The other thing is that the samples must be what we call independent. We haven't really talked about too much in terms of independence, but it just means that things don't depend on each other. And then finally, the variance of the population must be equal. So when we ran a t-test, we always ran an f-test first to make sure that this one was true. But we're not going to take the time to run an f-test between all our different options. So we're just going to, again, make that assumption. And let's just run ANOVA as a first sort of test. We go back to the F distribution when we are running the ANOVA test, which seems a little bit different because usually F distribution was always when we cared about variance. But that's actually, if you look at our original formula for variability or variance, our variance formula for a population was the summation of x minus mu squared divided by n. And so even though we are looking at variability, within that there is actually the mean value. So we are kind of looking at the mean within the context of a standard deviation. So ANOVA really is looking at the means, but we are using the F distribution to actually do that within our hypothesis procedure. So let's start at step 1 and sort of work our way through again. So hypothesis statements. So ANOVA is looking at the whether there's a significant difference in the means of more than two populations. So our alternative is that mu1, mu2, mu3 up to mu k, however many you have, are not all equal. At least one of them is significantly different. And then our null hypothesis is that they are all the same. Just a quick note is that your null hypothesis is what we're used to seeing, the equal to, but the alternative is slightly written in a different way. Don't use this one for your alternative. Mu1 is not equal to mu2 is not equal to mu3, because the ANOVA test just tests if one at least is significantly different. So these two could be about the same and this one could be different. So you don't really know which is which, and that's really not what a ANOVA test tells us. It just says that one potentially is significantly different than the others. Step 2, as usual, is our significance level, which is 5%, unless we know otherwise. There's no need to talk about one tails or two tails in ANOVA. That's not really the context of it. Step 3, we are going back to the F distribution, which means we need a degrees of freedom numerator and a degrees of freedom denominator. And they have formulas. Numerator is little k minus 1, where k is the total number of all the samples, groups, or categories. And then capital T minus little k, where capital T is the total number of all the items. So basically you add up all your sample sizes and basically just look at it as a big sample if you want to think about it that way. Step 4, drawing our sketch. We do go back to the F distribution. 0, 1 is around in the middle, and again, of course, we're going to create a critical region using our critical value from the F table. We're always going to look in the right tail again. Again, it doesn't make sense to talk about one or two tails, but we always generally, for an F, will look in the right tail. Step 5, again, is where things always sort of deviate with our formulas. So if you remember back to our F test, it was larger variance over smaller variance. In this case, it's still variance over variance, but it's variance between and a variance within, and they basically have their own formulas. So they look complicated, but it's not too bad. We know what the n values are, obviously, for each of our samples. We know how to find our mean, our x bar for each of our samples. We know how to find variability for each of our samples. The only thing that's a little bit different in this formula is this one right here, which is x bar bar, which is what we call the grand mean. So that's sort of an extra calculation that we have to do for our formulas. So the usual ones, n, x bar, standard deviation or variance, and then we have to calculate the grand mean. So the grand mean is exactly what it says. It's just the overall mean of all the samples, basically. So we denote it x bar bar, and it really is just taking all of your data, adding them up, dividing by how many you have. So it's like treating it like we don't have 3 samples, that we just have 1 large sample and finds the average overall. And just a quick note here, for calculating the grand mean, do go back to using your raw data. You can't average all your averages out. That's not how it works. So that's ANOVA as usual. If we're in the critical region, we reject. If we're not, we do not reject. So let's do a practice question related to ANOVA. So here's our question. The following are chlorophyll A concentrations for 4 different sites on Black Cat Lake. And here's our question. Is there a significant difference between the chlorophyll A concentrations from the different sites? So we're seeing the word significant difference pop up, and even though it doesn't explicitly say average or mean, that's really what we're comparing, right? The differences in chlorophyll A is more like the differences in the average or mean chlorophyll A. Again, another thing just to look at, how many sites do you have? We have 4, so that really means we're running ANOVA. If it just had 2 sites, we'd run an F and then a T, but again, because we have the 4 is why we're going to run the ANOVA test. All right, so let's start at step 1. So we'll state our hypothesis statements, null and alternative. So we would like to see, and we have 4 sites here, so mu1 is equal to mu of 2 is equal to mu of 3 is equal to mu of 4. So they are all equal to each other. And then the alternative is that mu of 1, mu of 2, mu of 3, mu of 4 are not all equal, or alternatively, at least one is significantly different. Step 2 is coming up with our alpha. So it doesn't say otherwise in the question, so we'll make the assumption that our alpha is 0.05. Step 3 is degrees of freedom, numerator, and degrees of freedom, denominator. And they have formulas, little k minus 1 and capital T minus k. So little k is the number of samples that we have. So either you can go to your hypothesis statements and count how many mu's you have, or you can just go say 1, 2, 3, 4 samples is what we're looking at. So little k is going to be 4. So 4 minus 1 gives me 3 degrees of freedom. And then capital T means the total number of all of your items in all of your samples. So basically you could look at the n of each of them and add them up, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So capital T is all of our data points. So 24 minus 4 gives me 20 degrees of freedom. And then we can take those 3 pieces of information, look up our critical value as always. And this is the first time we're repeating a table. So F test was F table, T test was T table, chi-squared test was chi-squared table. ANOVA is going back to an F distribution. So 0.05 at 3 over 20. So here's my 3. 3 over 20, I'm getting a critical value of 3.10. And then step 4, let's sketch our critical region. So F distribution is right skewed. So our critical value of 3.10 corresponding to probability of 5%. So we've created our critical region, let's test it out. And so step 5 is our test statistic. So F is S squared between over S squared within. and this is where these sort of bigger formulas come into play. So we are going to have to do quite a bit of work in terms of our descriptive statistics. So what do we need? We need an n value for each of our samples. We need an x bar value for each of our samples. We need an s squared value for each of our samples. And we're going to need a summation of x in order to find our grand mean, so just adding up our values. So again, in our calculator, this would be alpha 0, this would be alpha 4, this would be alpha 5 squared. And this one we've never actually done on our calculator, but it is alpha decimal place. So if you do go and look over the decimal place here, you can see the little summation of x. So again, I would expect you to be able to do each of those on your calculator. You can try them out if you want to and check, but they are on the next page just to save us a little bit of time. So the next page is just a summary statistics of all our different samples. So again, we have our n value for each, our sample mean for each, our variance for each. Notice there is a square on each of those already because it is variance. And then we have a summation of each. Just a quick note there that I have left these ones to actually just the sample mean and variance to 3 decimal places. So again, just make sure that even though we have a rounding rule for final answers, that if we are using a later formula like we are doing for hypothesis testing, that you want to keep at least 3 decimal places going forward. So in order to do our formula for s squared between, we need our n's, which we have, we need our means, which we have our k minus 1. The only thing that we don't have is the grand mean. So we're going to have to do that calculation first. So the grand mean is a summation of all of our x's all over t. So we already know that t is 24. We've already done that calculation. We could go back to our original data set and just add them all up if we wanted to. You could put them into your calculator all in one go and then hit alpha 4 if you wanted to. That would give you grand mean. I'm just going to sort of use our pseudo line here of sample sum. So I'm going to add up all of my sample summations. So 57.9 plus 37.5 plus 34.9 plus 38.1. That will give me my entire summation. And then t really is adding up my n values, which we've already done, but I'm just going to show in the formula that we can just add these up. So 7 plus 5 plus 6 plus 6. And again, just make sure you watch your brackets. I'm going to do it in 2 steps here. So we have 57.9 plus 37.5 plus 34.9 plus 38.1. So my numerator value is 168.4. And that's going to be divided by 24. So I end up with what we call our grand mean of 7.01666, and I'm again going to round it to 3 decimal places, so I'll keep it as 7.017. Ideally, you keep all of them. When we see how Excel does it, Excel will obviously keep all of them going forward, but I'm just going to keep 3 to make sort of my computation a little bit easier. So 7.017. So that's my overall average. So if you just averaged out all of these values together, that's really what the grand mean is telling us. It's just overall average there. Okay, so now we have our x bar. So it really is, at this point, substituting into our formula. So N1 is 7, x bar 1 is 8.271, and then we have our grand mean. So basically, we just do that for each of our categories. So 7, I'm just going to use my stuff over here. Our mean is 8.271, subtract our grand mean, so 7.017, and then we're going to square that. So that's for our first sample. Then we move on to our second sample. So 5, open a bracket, our mean in this case is 7.500 minus our grand mean. Square that, move on to our next one. So sample 3, we had 6 as our n value. Mean was 5.817. Square that, subtract your grand mean, then square it. And then finally our last one, so it's getting a little tight in here, 6 times our mean, 6.350 minus our grand mean 7.017, square that. So that's my numerator, all divided by little k minus 1. So we already know that k is our 4 samples. So we've already actually calculated that. That's our degrees of freedom numerator. So 4 minus 1 will give me 3 on the denominator. So I'm going to put the numerator and denominator into my calculator. So let's start with the numerator. So 7 times my mean, which is 8.271, minus my grand mean of 7.017. Oops. Close my bracket, square that, plus 5 times, open a bracket, 7.5 minus my grand mean of 7.017, close my bracket, square that, plus 6 times, open a bracket, 5.817 minus my grand mean, close my bracket, square that, plus 6 times, open a bracket, 6.350 minus my grand mean. So for my numerator, I'm getting 23.4833, etc. So that's my numerator, 23.4. Again, I'll keep at least 3 decimal places, 483 divided by 3. And I'll just do that while I have it in my calculator. So I am getting for my s squared between 7.828 to 3 decimal places. Ideally, you can keep more decimal places if you want to, but I'm just going to keep to that 3. So we're partway done our test statistic. We have our numerator. So now we have to do s squared within. It's a little bit easier to do as a formula. It's just your degrees of freedom times your variability for each of your categories or each of your samples. Okay, so I have my first one. It's my second one. So n1 minus 1, so 7 minus 1 gives me 6, but you can do your 7 minus 1 if you want to, times your variability, which is 2.139. So that's your first sample. Second sample, 5 minus 1 gives me 4, times my variability, plus 6 minus 1 times my variability, plus 6 minus 1 times my variability, all divided by capital T minus little k, which we already know to be 20, but remember it's 24 minus 4, which is my degrees of freedom denominator. So they show up again in my formulas. So let's put in those values. So 6 times 2.139 plus 4 times 2.825 plus 5 times 2.406 plus 5 times 1.123. So I end up getting for a numerator 41.779 divided by 20 gives me 2.08895. So again, I'm going to round that to 3 decimal places, 2.089. And that's my s squared within. So now I have my 2 values that I can put into my calculation here. So 7.828 divided by 2.089 gives me a F statistic of 3.75. So again, I'm going to go to 2 decimal places here just because my F table has 2 decimal places, not really a rounding rule. You can keep the extra decimal place if you want to. I'm just going to go at this point with 3.75. All right, so after all that sort of calculation work, we were looking at whether it fell in the critical region. So my test statistic is 3.75, which definitely does fall in my critical region. So this is a reject my null hypothesis, which means I support that there is a significant difference in at least one of the average chlorophyll A concentrations. So it's important to make sure your final conclusion references that at least one is significantly different. We don't know if they're all different. If one of them's different, the rest are the same. Again, that's not really what ANOVA shows us. It just shows us that first sort of step. So let's make our final conclusion. So 3.75 is greater than my critical value of 3.10. F is in the critical region. So therefore, reject null hypothesis and support the alternative. There is a significant difference in at least one of the average chlorophyll A concentrations across the 4 sites. So at least one of them is significantly different. So again, please make sure that that is in your final conclusion for anything related to ANOVA. If we did get a do not reject, you wouldn't have to say at least one, you just say that they're all the same. If we did go up and look at my means, one of these or at least one is significantly different. So it could be that X 3 and 4 are similar and then 1 and 2 are similar, or maybe they're all different, who knows. So again, that's why our hypothesis procedure will tell us at least one, and then maybe we can make a judgment call and come up with what we call a post hoc test, where you do another test afterwards to figure out which one is actually a significant result or not. So again, this is kind of nice because you wouldn't have to run an F and a T between all your different sites, that you could just do an ANOVA as a first step and then sort of delve a little bit deeper after the fact. That being said, the hypothesis procedure by hand is quite a long procedure. So that's why usually people would use a statistical software. So I'm going to show you how to do it in Excel, and this is actually going to be a lab, our final lab, lab 9 in the course. We'll be looking at running ANOVA on Excel. So this would be basically the output. I'm just going to quickly show it to you in Excel. So here's our same data set. The same one we did by hand. So this is our same values here, and I'm going to run my ANOVA procedure. So we're going to go to data analysis as we've done before, and then in our case we've done F-test, T-test. I want you to go right to the very top where it says ANOVA for single factor. There is something called ANOVA 2-factor, but that's not part of our course. We're always going to be working on the single factor one. So I'll choose that option. Input range is all your original raw data. So I'm going to highlight all my data in one go. So site 1 to 4. I did include my labels, the first row there. So I am going to check labels in the first box. You can adjust your alpha as appropriate. So I'm going to leave it as 0.05. And then my output, I'm going to put mine just in B11, and we'll see what the output gives us. So input all in one go, check that labels if appropriate, change your alpha as appropriate, and then where you want it to go in your file. So let me just adjust my screen a little bit for you. So this is my output for my ANOVA. Okay, so you'll notice that they give you a summary statistics table here. So for site 1, we have our n value, we have our summation of x value, we have our averages, which is our x bars, and we have our variance values, which are s squared. So these are the ones that we calculated previously as well. And then down here we really have our ANOVA piece. So we have our between group, our within. It talks about SS, which is the sum of squares. These are our numerators. And then we have our degrees of freedom. That's our numerator denominator number. So basically what we're doing is we're taking our numerator, divide it by 3, and this number gives us s squared between. And same thing, numerator divided by 10 or 20 gives us our s squared within. If you take these two and divide, that's how we're getting our F statistic. Ours is just rounded to 2 decimal places. Our critical value is 3.10, which again rounded to 2 decimal places. And then P, as usual, is what we compare to alpha. So on your notes, you do have that same output here. So that's the same thing. I just rounded these ones as we had them rounded. So our numerator number divided by degrees of freedom gave us s squared between. And then same thing, numerator divided by our degrees of freedom, s squared within. And then dividing these two numbers gives us our F statistic. And then obviously our p-value is less than 0.05, so that would also give me a reject if I look specifically at that one. So let's do one more question where we're actually just looking at the output rather than doing the full ANOVA test. So here's our next practice question. So the following data is measurements on the lifetime of biodegradable material in months for 4 different landfill sites. Decide whether or not the landfill site has any effect on the lifetime of biodegradable material. So we'd really like to see if the average difference, if there's an average difference between each landfill site in terms of how much stuff biodegrades. So again, since we're looking at 4 different sites, we're going to be running the ANOVA test. We have all of our raw data here, so you could put that into Excel and then run the following from Excel. And we still want to run the full test, but we can utilize our information here. So let's start at step 1 and work our way through as always. So step 1 is our hypothesis statements. So we have 4 again, so mu of 1 is equal to mu of 2 is equal to mu of 3 is equal to mu of 4. Mu of 1, mu of 2, mu of 3, mu of 4 are not all equal. Step 2 is our level of significance, so alpha is 0.05 unless we know otherwise, and it does specify that one right in the question. Step 3 is degrees of freedom numerator and denominator, where numerator is little k minus 1 and our denominator is capital T minus k. Little k would be, we had 4 different landfill sites we're looking at, so 4 minus 1 gives me 3 degrees of freedom numerator. And then capital T is our total number of all of our samples. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19, 20, 21, 22. Alternatively, we could have just gone to our N column and added these guys up to give me 22. So 22 minus 4 gives me 18 degrees of freedom. And again, we didn't really have to do those calculations, because if we look at our Excel output, it does give it to us right here. So let's find that in our table. So 0.05, 3 over 18. So 3 over 18 in this case. So I am getting a critical value of 3.16 coming out there. Step 4, we can sketch our diagram. 3.16, and that corresponds to 5%. And then our test statistic is S squared between over S squared within. And again, remember, this is our numerator divided by degrees of freedom. This right here is our S squared between. And within group, this is our denominator. Okay, so let's put that into our calculator. So 12.12477 divided by 1.275449. So I am getting around, if I'm going to round to 2 decimal places, 9.51. Which is definitely in my critical region, way up here somewhere. So I do again have a reject my null hypothesis. There is a significant difference between at least one of the 4 landfill sites. So this is greater than my CV 3.16. So therefore, reject the null hypothesis and support your alternative. So I'm rejecting the null. I support that there is a significant difference between at least one of the landfill sites. So there is a significant difference in the average time to biodegrade for at least one of the landfill sites. So always bring it back to your original question and make sure that we do answer that original question. That's what they were asking. Does a landfill have an effect? In this case, we said yes, it does. At least one of them is significantly different. So if I went the next step again, let's take a look at my averages. They all look quite similar, but we are seeing a significant difference. So maybe 1 and 4 are about the same and 2 and 3 are about the same. But again, that would be another hypothesis that we would need to check in some capacity.